All right, so let us start our seminar. Our today's speaker, Maley Bannerjee from Indian Institute of Technology in Kanpur. And the topic of today's talk is structural sensitivity of global bifurcation structure in Gastингса-Пауэлла model. Please, Maley, you can begin your presentation.
Okay. So thank you very much, Vitaly, for invitation, and also Anastasia for this invitation to talk about this. So this is a new topic, means not pretty much new in the area of mathematical biology, but it is new to me, and I found some interesting result, and that I want to discuss with you. And towards the end, I will also discuss something about future direction of research. And I'll also mention that at some point I get stuck and I don't know how to proceed further, but let us start with the topic. So first I'll talk about what is Gastингса-Пауэлла model, and mainly I'm interested to look at the chaotic oscillation in Gastингса-Пауэлла model. Then I'll discuss the complete bifurcation structure of the Gastингса-Пауэлла model. And then I'll come to the most important part, that is what is structural sensitivity. And then I will go by global bifurcation and finally future direction of research and as well as references. Okay, so Gastингса-Пауэлла model is a well-known classical model which first introduced to capture chaotic dynamics in a three species interaction. And in terms of dimensionless variable and parameter, model is described by these three equations. So first equation is for prey population. Second equation is for intermediate predator, and the last one is for the top predator. So it is assumed that in the absence of middle predator, prey population follows logistic growth law. So in dimensionless variable, it comes out to be x minus x squared, and grazing of prey by the middle predator and grazing of the middle predator by the top predator, they follows the same type of functional response. I'm not mentioning same functional response, rather same type of functional response. And those functional responses are Holling type 2 functional responses, which are known as saturating functional responses. And both the predator population suffers from intrinsic linear death. Those are represented by D1Y and D2Z. And functional responses are described by A1x by 1 plus B1x and A2y by 1 plus B2y. And for this parameter set is close to the parameter set used in the paper by Gastингса-Пауэлла, but precisely it is taken from one paper by Yorgis, and they have shown that if you specific initial point at the interior of the first quadrant, then after some initial transients, trajectory will converge to this chaotic attractor. Now the question is that for this problem, we can find out different equilibrium points, different invariant sets, and for feasibility in terms of ecological system, what we need, that all the variables should be confined within the non-negative range. So that means x, y, z, they are all required to be greater than equal to 0. So of course, there is a trivial equilibrium point, there is an axial equilibrium point, there is a boundary equilibrium point, and what about their stability? More precisely, we can ask the question, is there any possibility to have more than one attractor for this parameter set? Answer is yes. For these parameter set, if we thoroughly look at the dynamics of the model, so what we can find in the interior, there is a chaotic attractor, and on the boundary plane, that is xy plane, there is a stable periodic solution. Now this terminology, stable periodic solution, is a little bit tricky, because in this case, this stability is conditional. Conditional means if we start from any point on xy plane, of course, for xy both greater than equal to 0, precisely both greater than 0, then trajectory will converge to this limit cycle. And this is a typical parameter set for which one can check all the equilibrium points are unstable. So trivial equilibrium point 0, 0, 0 is unstable. Predators free equilibrium 1, 0, 0 is unstable. Top predator free equilibrium of the form x, y, 0, that is also unstable. And finally, there exists interior equilibrium point x star, y star, z star for this choice of parameters. That is also unstable. But due to the dissipativeness of the model or dissipative property of the model under consideration, there are attractors and solutions cannot grow unboundedly, and thorough numerical investigation reveal there is a stable limit cycle on xy plane and a chaotic attractor. It has a non-empty basin of attraction. Now, if we look at the numerical simulation of two different models which shows chaotic dynamics, as it was pointed out by Alan Hastings and his co-author, this paper is recently published in Royal Society Interface. They have explained that there are two types of irregular oscillations. Of course, both are irregular oscillations. One can debate that, okay, both of them are chaotic or not. But what is the precise demarcation between these two figures? On the left, what we can see that population remains close to 0 for a significantly longer time interval rather than what we can see on the right hand panel. On the right hand panel, one can easily verify that as of now, not for a single time point, population reaches the 0 value. It is close to 0, but not exactly equal to 0. From here, it seems to be 0, but those are not exactly equal to 0. Why? Because the model always, these kind of models satisfy the condition that this is invariant with respect to the 0 axis or 0 plane. So if one of the population goes to 0, there is no provision to return back to some non-zero value. So for visualization, it seems at some time they might be equal to 0, but practically they are not exactly equal to 0, but they are close to 0. So ecological interpretation is that left-hand time series indicates there is a possibility of extinction. On the right-hand time series, it does not show any indication as of now, except only at one time point at this level, that there is a possibility of extinction. But in case of Hastings-Pawell model, just look at this value. Earlier, if we just change the value of D2 slightly, earlier figure was for 0.081. Now, if we choose D2 equal to 0.08, what we can see, once the trajectory started from an interior point of the first octant, it remains chaotic for certain time period, and then it starts moving downwards and ultimately converges to the limit cycle lying on the xy plane. if we look at the time series of 3 components against time, then we can have these 3 different plots. Blue one corresponds to prey, red one corresponds to middle predator, and jet magenta color corresponds to top predator. And what we can see that up to t equal to 5000, there was no indication of possible extinction of the top predator. But ultimately, if we perform our numerical simulation for a longer time, that means beyond 5000, then we can see all of a sudden this trajectory starts moving downward and top predator goes to extinction. And this kind of chaotic behavior is not exactly labeled as only chaotic dynamics. Rather, precisely it is labeled as chaotic transients, because final destination of the trajectory is the limit cycle on xy plane. So therefore, this part, that means what we can see up to t equal to 5000 plus some time point, those are actually chaotic transients. And ultimately, top predator goes to extinction, and x and y component, they remain in oscillatory mode. The oscillatory mode is not clearly visible from this picture because there are so many frequent oscillations. But if anybody interested, they can zoom in to this portion and they can see that smooth periodic solution in this particular region. Now the question is that how this kind of scenario can appear, that I am going to discuss with the bifurcation structure. And next I will come to the point that whether this kind of dynamics is structurally sensitive or not. Once I'll go to the structural sensitivity part, then I'll provide the ecological interpretation or justification or motivation behind this kind of investigation. So first of all, let us look at the bifurcation structure. I am not going to show you here the detailed, boring mathematical calculations. Rather, what I can just mention, I can try to explain you the different type of bifurcation takes place that can be explained through this bifurcation diagram. So this bifurcation diagram is plotted with respect to the parameter D2, keeping all other parameters fixed as I have shown earlier. And on the vertical axis, here either the components of equilibrium points are plotted or the maxima or minima of the limit cycles are plotted. And in case of 2 periodic, in case of 4 periodic, and in case of chaotic oscillation, all local maxima and minima after discarding initial transients, those are plotted here. Now, proceeding in a different manner, so I'm going to explain that what kind of bifurcations takes place one by one if we start from a value of D2 from the right hand side, not from the left hand side. So if we choose D2 somewhere here, that is a value, say 0.108 or say 0.11, there is no interior equilibrium point because these are the components involved with the interior equilibrium point. And here what we can find only the limit cycle on the xy plane that is stable, and the components of limit cycle, that means maxima and minima of the limit cycle on the xy plane, those are plotted in black color. So this black straight line is the maxima of the limit cycle on the xy plane corresponding to the x component, and this black line, thick black line at the bottom, it also corresponds to minima of the limit cycle. Then once D2 is equal to 0.10496, two interior equilibrium points, those are generated through a saddle node bifurcation. And interestingly, both the equilibrium points are unstable. Then at D2 equal to 0.10407, all these results are correct up to 5th decimal places. What we can find, there is a subcritical Hopf bifurcation. Due to subcritical Hopf bifurcation, one unstable cycle emerges, and this unstable limit cycle is marked here with this magenta color. So these two branches corresponds to unstable limit cycle generated through subcritical bifurcation, and one of the interior equilibrium point becomes stable through Hopf bifurcation. Again, this stable interior equilibrium point loses stability through another Hopf bifurcation, which takes place at D2 equal to 0.0945, and this is a supercritical Hopf bifurcation. And due to the supercritical Hopf bifurcation, what happens? One stable limit cycle emerges that is marked in blue color, and these periodic solution undergoes successive period doubling and ultimately arrives at a chaotic regime. Then we can find a periodic window. Again, chaotic dynamics returns, but all of a sudden what we can see that these chaotic dynamics disappears as we can't see any branch continued beyond this point in blue color, and it again regenerated at some threshold here, and again you can see some sort of branches corresponding to the chaotic oscillation. And what we have checked for this region, that means over this entire range of the parameter D2, there is no chaotic or coexistence scenario in the interior of the first octant all the time predator population goes to extinction. Now we have to understand why this kind of disappearance and reappearance takes place here. This kind of disappearance of chaotic dynamics resulted in due to basin boundary collision. So what is the concept of basin boundary collision? Hypothetically, we can think about in terms of X component. Of course, they are combined with the appropriate choice of Y and Z. This unstable limit cycle can play the role of, or it is actually playing the role of separatrix between the basin of attraction of these two periodic cycle or stable equilibrium and this limit cycle in the XY plane. And once this particular chaotic attractor hits this unstable limit cycle, so therefore trajectory can reach within the basin of attraction of the limit cycle in the XY plane, and then it moves towards the limit cycle lying on the XY plane. And same kind of phenomena repeats at this particular threshold, and through which this chaotic dynamics regenerated. Now, just for your information, quickly I can show you that some results can be obtained. And what we did, we have chosen the model in most general form in the sense that we are considering this system in terms of f1 tilde x and f2 tilde y. By solving these equations, we can find out the coexistence equilibrium point. We have given a lot of mathematical condition, and I am not going into that details, but we can prove under certain condition, we can ensure there exists at least one feasible coexistence equilibrium, and under certain particular parametric restriction, this model also admits two interior equilibrium points, as we have seen in the previous bifurcation diagram. And this f tilde j, this stands for FJU divided by U, because these FJs, they corresponds to Holling type 2 functional responses. So in one case, it is A1x by 1 plus B1x. So F tilde U means actually A1 by 1 plus B1x. Similarly, F tilde 2 stands for A2 by 1 plus B2y. And then under certain condition, we have actually proved that two interior equilibrium point can collide, and they can give us some kind of idea that, okay, under certain condition, two roots of this system can collide. And with this general form, if we calculate the Jacobian matrix, then Jacobian matrix takes this particular format, and the derivation of components of coexistence equilibrium at the saddle node bifurcation threshold satisfies these conditions. That means Sn f1 dot tilde x Sn equal to -1, and this expression actually implies determinant of this Jacobian matrix is equal to 0. Because if we just want to expand the determinant in terms of this last row, so only one non-zero element is this one, and then determinant will be this quantity multiplied by these two minus multiplied by these two. So this is 0, and as at saddle node bifurcation threshold this relation holds, so it implies these quantities also equal to 0. So therefore at saddle node bifurcation threshold, delta J of Esn, it is exactly equal to 0. And using some other tedious calculation, we can show that lambda equal to 0 is a simple eigenvalue, and therefore it is a candidate to check whether saddle node kind of bifurcation is taking place or not. So in order to confirm, we need to verify the transversality condition, and transversality condition can be verified like this. We can calculate two eigenvectors V and W, which are the eigenvectors corresponding to 0 eigenvalue of the Jacobian matrix and its transports at the Hopf bifurcation threshold, and then we can verify these two conditions, which are known as transversality condition. Depending upon the properties of the functional form, that is F1 and F2, we were able to prove that W transpose F D2 this quantity not equal to 0, and also this quantity not equal to 0. Anyone is interested to go into the details of this condition, they can look at the book by Parko, and it is actually Sotomayer's theorem, which ensures that lambda equal to 0 for the Jacobian matrix evaluated at a particular threshold indicates it is a saddle node bifurcation, and of course it is a non-degenerate. And conclusion is that for here, that coexistence equilibrium point undergoes a non-degenerate saddle bifurcation at D2 equal to D2 Sn. So similarly, we have proved the Hopf bifurcation and little bit about the stability of the limit cycle, and mostly we have verified the stability of the limit cycle in terms of finding first Lyapunov number numerically. Now we come to the most interesting part, that is structural sensitivity. So what is structural sensitivity? Just holding type 2 parameterization, we wish to mention what are the conditions required to be satisfied by these functional responses. So those conditions are given by this list. So at 0, these functional responses should be equal to 0. So that means if there is no prey, nothing to predate, these functions are monotone increasing. So that means with the increase in the population density of prey, there will be an increased predation. But of course, this rate of predation will not grow unboundedly. So therefore, functional response are saturated, and that actually characterized by the existence of finite horizontal asymptote. Condition is given by this one. And also one more assumption, this is concave down. And now what we are going to do, we are just going to consider two different parameterizations for these functional responses. So which are such parameterization? One is Holling type 2 and another one is Ivy functional response. And you can check all the conditions mentioned here, those are satisfied by both these functions. So at u equal to 0, both of them are equal to 0. Their first derivative always positive, and limit u tends to infinity fju, both of them are actually finite quantity, and their second derivative is always negative. And now our idea is that we just want to check if there is a little bit change in the grazing pattern, whether this change will affect the bifurcation structure or not. Because as a people like us who are interested in mathematical modeling, we set up a rule that all the time predator will predate prey following this parameterization. That might not be true. Rather, they are following some kind of evolutionary approach. With the advancement of time, there might be a change in the grazing pattern. And what we are interested to check, that keeping all the properties of the functional response unaltered, if we slightly change the parameterization of the functional response, whether this change will affect the resulting or existing bifurcation structure or not. So how the bifurcation structure affected by the change in parameterization of the functional response or not. Now the next question is that, okay, for this problem, following the Gastings-Pauwel, even by the Iorgis paper, you have some guideline about the choice of AH and BH. Now, how to choose the parameters for the Ivy functional response? So first of all, I must mention that for two functional responses, for the predation of prey by the middle predator and predation of the middle predator by the top predator, for Holling type 2 parameterizations are like this, and for Ivy they are represented by A1 bar, B1 bar, and etc. Now these are the parameter values, mainly A1, B1, A2, B2. They are given in the paper, and we are considering these parameter values, and then we use some nonlinear least square method just to estimate the parameters A1 bar, B1 bar, A2 bar, B2 bar in such a way within a admissible range of values of X and Y, two functional forms remain close to each other. For clear-cut visualization, here you can see this blue curve corresponds to F1HX. So that means Holling type 1 functional response with A1 equal to 4.98 and B1 equal to 6.2, and red curve corresponds to F1IX, where A1 bar and B1 bar is equal to 0.67 and 5.349, such that within the range 0 to 1, these two functional form remains close to each other. Of course, one can ask the question, if I consider X larger than 1, whether those parameter values remain unchanged? Answer is yes. Answer is no. Depending upon the range, what we want to consider, that is up to X equal to 2 or X equal to 10, we need to re-estimate those parameters. Then next question might follow, that why we are restricting ourselves X within the range 0 to 1? Because with some preliminary mathematical results and mathematical inequality, we can actually show that all the time attractors will appear within a convex domain for which maximum value of X will be 1. In particular, what we can say mathematically, that we can prove analytically, limit supremum as t tends to plus infinity, xt will be always less than equal to 1. So that is why we are considered here X ranging from 0 to 1. Now the point is that we want to check that for these two different parameterization, what are the bifurcation structure. Also, we need to mention that reason behind such kind of closeness of two functions also ensures that there should not be drastic shift in the position of the coexistence equilibrium points. So coexistence equilibrium points should be close to each other such that these two functional forms are chosen very close to each other. Now, if we look at the ecological interpretation, in this paper, you can see they have actually explained, depending upon the available prey density, what is the grazing rate. They have collected some data, and these blue dots are actually data points, and these three functional response they have fitted Holling type 2, IVLF, and trigonometry. So far as my knowledge goes, this is the only literature where you can find that fitting of these three functional responses against real data. But this actually ensures that there is a provision. Once we have one parameterization like Holling type 2, just to check the structural sensitivity of the model, we can consider some other parameterization also, and they fits well with the rate of predation data for ecological species. Now, if we look at the bifurcation structure, so these three figures corresponds to the bifurcation structure for three different components. This one corresponds to X component, this one corresponds to Y component, and this one corresponds to Z component. So from all these three figures, we can understand that X component of the chaotic attractor hits the unstable limit cycle at this threshold, of course the lower branch, because you can see that upper branch is little above of this one, and this is some sort of illusion because we have projected the three-dimensional structure over two dimension. Similarly, for Z component, the minimum of the attractor actually hits the unstable limit cycle. But for Y component, you can see if we have a closed loop, that means if we zoom in this particular portion, we can see the maxima actually hits the unstable limit cycle. And here one can check that this component of the interior equilibrium, that is corresponds to Z, this actually coincides with the value 0, and this indicates that interior equilibrium point can generate through a transcritical bifurcation of the boundary equilibrium point. But precisely, this is the bifurcation structure of three components, and it clearly indicates due to basin boundary collision, the top predator will go to extinction, because for all three components, we can see X and Y, they have some other attractor which are non-zero, which corresponds to these two horizontal line for the plot of X component, and these two horizontal line corresponds to Y component. But for Z component, there is only one, that is 0. So it clearly indicates over this range of parameter, top predator goes to extinction. Now the interesting point is that this is the bifurcation structure with Holling type 2 functional response. If we choose IVLF functional responses, that means which are close to each other, then you can see there is a drastic change in the bifurcation structure. And here for X component, Y component, and Z component, we can see there is no possibility of extinction of the top predator. And this is called the structural sensitivity. So if we change the parameterization a little bit, mathematically, we can explain that, okay, instead of Holling type 2, we can consider IVLF, but ecologically, it can be interpreted as with the advancement of time or after a couple of generations, there might be some sort of evolutionary change in the grazing pattern. That is why at some time point which was well described by the Holling type 2 functional response, that might not be true for all future time, and such kind of small change in the parameterization of the functional response, once we look at the complete bifurcation structure, reveals a drastic change in the bifurcation structure, and which means that possible prediction of the extinction of the top predator may be false, and that can be explained as a structural sensitivity of the model, because it clearly indicates that small change in the parameter value results in survival prediction about the top predator. Not only just survival prediction, rather what we can see, interestingly, if we look at the nature of the solution for the Z component for same parameter threshold, where Holling type 2 functional response indicates extinction of the top predator, but IVLF functional response actually indicates multi-periodic oscillation, and that you can see from this picture. So this is the plot of Z component against T for both the functional response and Holling type 2, and right one is the plot of Z component against T for the IVLF functional responses. And now, before going to the conclusion part, let me give you one more idea or one more interesting scenario that we have checked by varying some of the other parameters, because here up to this point bifurcation structure is obtained by varying D2. So one can raise the question, if you slightly change the another parameter D1, how it will affect the dynamics. So for that purpose, what we have done, we have considered D1 equal to 0.45. Earlier it was some other value D1 equal to 0.4. And in this case, if we slightly change D1, then even with Holling type 2 functional response, there is no possibility of extinction. So those kind of extinction threshold, in some sense, interesting, because it shows some sort of transient chaos and ultimately leads to extinction of the top predator from the deterministic analysis. But I am not saying that all the time structural sensitivity of the model is responsible for having a different kind of outcome after a long time. That might be due to some sort of change in the environmental condition or some sort of change in the demographic. But in order to predict the extinction of a population, we need to check a wide range of parameter set just to ensure whether the structure remain invariant with respect to small change of other background parameters or not. And here, interestingly, we have observed a nice scenario. So in this case, with Holling type 2 functional responses, there is no prediction about the extinction of any one of the component. But with similar estimation of the functional response parameters, what we observe that again, none of the components shows any kind of extinction. But as of now, we did not explore. But if you look at this part, of course, it is not clearly visible to you. As we have constructed the figure, we can clearly understand. But let me try to explain. Probably you can see that there is a bend of this particular curve. So some sort of reflection of S-shaped curve. One part is in blue, then a connecting part in magenta, and then the remaining part is in blue. So here what we have observed, that there is a saddle node bifurcation of two periodic cycle. We are interested to explore this scenario in more details, that how this kind of scenario can appear, because in literature people have studied at some time saddle node bifurcation of periodic solution, but this is a two successive saddle node bifurcations of two periodic cycle. Because for the blue part, you can see this is one component, second component, third component, fourth component. So they corresponds to 2 periodic cycle. Similarly, for this part, we have also the 2 periodic cycle. So what is observed that with the Ivy-Lev functional response, D1 equal to 0.45, we have a tri-stability. One of them is the attractor in the XY plane, which are marked in black color, and two periodic cycles. And we need to investigate it in detail, that how such kind of scenario has appeared for this model. And this is all about my today's talk. So all the details you can find in this particular paper. So my entire talk is based upon this paper only. But at the same time, I want to draw your attention in two more work here. So this was done for only a pre-predator model. But in this case, what we did, we did not estimated the parameter in such a way that two functional response will remain close to each other. Rather, what we did here, suppose Holling type 2 functional response is given by a1x by 1 plus b1x, and then we have considered Ivy-Lev functional response as a1 into 1 minus exponential minus b1x. So with that approach, we have analyzed the pre-predator model with alley effect in predator and reported different kind of bifurcation scenario and how those bifurcation scenario are structurally sensitive or not, we have explained there. And in this paper, this is quite interesting, we have considered a 3-component model. We have analyzed the dimensionless version. Then we tried to find out parameter set for the original model having the dimension such that there is one-one correspondence between all possible local and global bifurcation that we observed for the dimensionless model is valid for the model with dimension. Because one can raise the question that, okay, here your prediction about the chaos or prediction about the extinction of the top predator after some chaotic transients based upon the assumption that growth rate of prey and intraspecific competition rate for prey, they are not only equal, rather they are equal to exactly 1. So if we remove this assumption, whether results will remain invariant or not, or same conclusion will hold or not, that remains an open question. Apart from that, there are several future directions that I am now going to explain. So of course, one can look at different type of model and perform similar kind of analysis. That means structural sensitivity for the models with partial differential equations, delay differential equation, stochastic differential equation, model with multiple time scale, model with non-smooth reaction kinetics, and models for critical transitions. As of now, so far as my knowledge goes, models with critical transitions or extreme events, they are studied with the help of, or for the model, authors have provided emphasis on saddle node bifurcation of equilibrium point. But there is very few literature where the saddle node bifurcation of limit cycle, or as I have shown here in case of Ivy-Lev functional response, we have saddle node bifurcation of 2 periodic cycles also. Those are whether related to such kind of critical transitions or not, that will be some interesting research direction. But most challenging one is that if we want to examine similar kind of structural sensitivity for models with other functional response, what would be its parameterization? Because as of my knowledge goes, in the context of ecological literature, Holling type 2 functional response, Ivy-Lev functional response, and trigonometric functional response, which is actually A tan hyperbolic bx, these three are already reported for different type of interaction of ecological species. Now, my thought is that, and the problem with which I started thinking during last couple of months, that instead of holding type 2 functional response, if I wish to consider holding type 3 functional response, non-monotone functional response, holding type 4 functional response, Beddington-D'Angelis functional response, and the Crowley-Martin functional response, as well as functional response for 2 prey, 1 predator, what would be the equivalent choice like Ivy-League functional response or tan hyperbolic functional response? Because as of literature I have searched, there is no such functional form equivalent to these functional responses. Of course, mathematically we can construct some functional form, that means such that property will remain invariant, and for appropriate choice of the parameter or estimation of the parameters, they will remain close to each other. But one group of researchers will raise the question, can you derive these functional responses mechanistically? Frankly speaking, I don't know how to answer those questions. So this is the work mainly I did with my current PhD student Indrajyoti, earlier PhD student Swadesh, and she was a summer intern for me for a very brief time, but she actually checked a lot of initial simulations, because if you ask me the question, how you determined the second parameter set, that is D2, D1 equal to 0.45, so credit goes to her. These are the references. So these two are classical book for bifurcation theory. These are some of the references related to this type of work, and the reference marked in magenta color is the reference from where I have presented my today's talk. Thank you very much for your attention.
Yes, thank you, Maley, for this interesting presentation. It's really always interesting to discuss this complex nonlinear dynamics. So we have some time for discussion, and I would like to begin with the roots to chaos. Could you please show this one of this bifurcation diagram, maybe the first one you showed in one of the first slides?
Can you see the slides?
Well, not yet. So yes, there are slides, but not.
This one?
No. Where you show this bifurcation, this period doubling, this. Yeah, maybe. This one. Okay, for example, this one. So indeed, in the beginning, we see this at least 2 consecutive period doublings.
Yeah.
But it's less clear what happens after that. Do you observe this period, next period doubling bifurcation?
Yes, we have actually checked the successive period doubling, and this period doubling threshold satisfies the Feigenbaum constant, but those successive period doubling takes place over a very narrow parameter regime. So this bifurcation diagram is prepared with an increment of this parameter value D2 with 0.001. So in order to clearly visualize and identify all those successive period doubling before reaching to chaos, we need to construct the bifurcation diagram with increment of D2 at least 10 to the power minus 6. And and precisely answer to your question is that we have checked, and there is successive period doubling, and as per this picture that is not very much clear, because it shows some kind of stiffness. So successive period doubling thresholds, they differ from each other at the order of 10 to the power minus 9, 10 to the power minus 10, something like that.
Right. But usually, what is also well known from this classical works is that after this period doubling bifurcation sequence of period doubling bifurcations, you can have other periods like 5, 7, 3, and this is usually the indication to transition to chaos.
Something can be observed here also. So here you can see some sort of hollow region, and here we have a period 3 cycle. So that means 3 periodic window is available here.
Yeah. Yes. Then you have, well, again, it's not in all problems you have this exactly the same. I mean, all of these intermediate steps, but you can have like 3 times 2 power n, 5 times 2 power n, and so on. This is, you understand? Yes, what I'm
yes.
saying.
But
this can be,
we did not explore that part here.
Yeah. All right. Well, by the way, to our audience, if you have questions, you can ask. Waiting for other questions, I will continue with my some comments about this. What was also very interesting about this collision between this chaotic attractor with the unstable limit cycle.
Yeah.
You explained that, but maybe I missed to make it more clear. Do you really have that? So how it happens, in fact, you have a part of the chaotic attractor which approaches the whole limit cycle, or how it happens in more detail? Can you explain it easily, or this is not
actually that figure is not presented here, but your question is perfectly all right, and probably it would be better if we can show such kind of 3-dimensional diagram. So just from this figure we can just try to understand. So this is the component X of the chaotic attractor, this is the component Y of the chaotic attractor, and this is component Z of the chaotic attractor, and these are the branches of the unstable limit cycle. So as per your question, it would be better to show these chaotic attractors along with this unstable limit cycle in 3-dimensional space.
Right.
Practically, this unstable limit cycle plays a rough role of the separatrix between 2 attractors, because as I have mentioned that on XY plane there is a stable limit cycle, it has a non-empty basin of attraction, and also interior chaotic attractor, it has also a non-empty basin of attraction. And mainly what I wish to explore in near future, that how the basins of these 2 attractors change with the change in parameter value. We did not explore in detail because I don't know how to perform parallel computing, but in order to come up with a very nice and clear-cut figure for such basin boundary or basin of attraction, we need high performance computing facility in order to come up with the clear-cut idea that how the basins are getting altered or changed. But roughly what we explored, there is a riddled basin, so there is no single smooth curve which demarcate the basin of attraction for limit cycle in XY plane and the chaotic attractor in the interior of the first quadrant. Rather, it is a riddled basin. So there is a serpentine kind of structure of basin for one attractor that is actually supported by or complemented by the basin of attraction for the another attractor on the XY plane.
Yes, right. But it would be really interesting to see in 3 dimensions how this attractor approaches the limit cycle. Because from this figure, I understand, well, it's a limited information about the maxima and the minima of these installations, but the whole limit cycle, how it interacts with attractor, it would be very interesting to see. And also in relation to this question, so this is for Holling type 2 functional response, you have this interaction. But for Ivlev functional response, is there this unstable limit cycle and they just do not intersect with the attractor, or there is no limit, or there is no limit cycle at all, or it's impossible to say? What do you think?
Actually, in between, connection got disrupted. So could you please repeat your question?
Yeah. In the case of evolve functional response, do you think there is also an unstable limit cycle, but they don't meet with the attractor, or there is no limit cycle?
Because this magenta color curve is the unstable limit cycle there, and this unstable limit cycle actually merges with this stable limit cycle on the XY plane. So there is a saddle node bifurcation of this unstable limit cycle from interior and stable limit cycle on the XY plane. So there is this unstable limit cycle. So this existence of unstable limit cycle is not structurally sensitive, but the collision of the chaotic attractor with the unstable limit cycle, this is structurally sensitive.
Yes, but my next question is indeed about structural sensitivity, because I think that we might need a definition of structural sensitivity, because usually, you consider a small change of your function. So, I mean, sufficiently small. So, in the mathematical sense, meaning that there is for any positive epsilon and so on and so forth. But you just take two different functions. Okay, they are not very far. They are quite close, and you showed the graph where they indeed quite close. But they're fixed in the sense that you don't consider a sequence of functions which approach each other. So what I'm trying to say is that if you have a function dependent on some parameter epsilon, for example, or whatever we call it, so when this parameter changes, you have a continuous transition from one function to another function. Then, when they are really sufficiently close, and we don't know what means sufficiently, you just tend this parameter to something, to zero, for example. So in this sense, structural sensitivity, not just two functions which are close to each other like visually, but in more mathematical sense, that the difference between them converges to zero as some parameter goes to zero. Yeah.
So for that, we need to follow the approach that was presented in one of the paper by Bob Cui and Jean-Christophe Poggiale. They have considered that lambda times Holling type functional response plus 1 minus lambda times Ivy-Lev functional response, and then they change lambda from 1 to 0 or vice versa 0 to 1, such that we can transit from Holling type 2 to Ivy-Lev functional response, and just to identify at which threshold this disagreement appears.
Yes.
Yeah, that's true. That's true.
And in general, can we say that if the difference, if we consider the structural sensitivity in this sense, that the difference between these two functions is sufficiently small, can we say that, that attractor also is continuous with respect to this parameter?
That we have to check. Because that part I never checked for this model. So we because frankly speaking, for that I need a devoted research scholar who mainly focus on this work. So most of us did as a part-time job for this paper, and as of now I can't provide any definitive answer.
I understand. But in general, in the literature, because I don't know sufficiently well this topic, but in general, in the literature, what is known? So shall the attractor be continuous as a depending on the parameter, or it is not necessary?
Yeah, in this case, what we can say roughly that this is mainly due to parametrization. So that means change in functional form, because we checked with the fact that if we consider a1 plus epsilon x by 1 plus b1 plus say eta into x, we change slightly a1 and b1, that will not give us any such kind of drastic change. But drastic change is observed here only if we replace the Holling type 2 functional response by Ivy-League functional response.
All right. So probably my last question is about this very intensive. Again, I come back to this collision between chaotic attractor and unstable limit cycle. If you show this previous diagram, which we discussed just before, yes, this one. So this attractor disappears, and in fact, there's this partial extinction of one of the predator extincts, and the solution goes to the XY plane. Yes, and at this XY plane, you observe a limit cycle. So what I'm trying to understand, if you consider this limit cycle at the XY plane, can we say something about its stability? I mean that in this interval, if you look at these figures for the value of G2, like I don't see very well between 0.65 and 0.8, 0.08. So can we say that in this interval, this limit cycle is on the XY plane is stable, but outside of this interval, it is unstable? Is it true?
Numerically, we have checked that for this range of D2 value, so that means if we consider the value of D2 from this range to this range, so we can say with respect to the first octant, the limit cycle on the XY plane is globally attracting. And as per my knowledge is concerned, I don't know how to prove it mathematically, because we have chosen different initial conditions by fixing z, say z equal to 0.1, and different initial choice for x and y, and check all the trajectories converging to the limit cycle on the XY plane. Then we change z equal to 0.2 as well as 0.05, 0.01, and all the points, if we start and if we consider the initial points from any interior, all the time trajectories are converging to the limit cycle on the XY plane. So numerically, so far we have explored, we can say that yes, the basin of attraction of the limit cycle on the XY plane is the entire first octant. And I must repeat it again, this is just numerical observation.
Yes, but if you take outside of this interval, it remains stable, but not globally stable, but locally it remains stable, right?
Yes,
outside of this.
Yes, okay. Yes, because so, once we have a point on the limit cycle, then we have checked. Suppose we choose one point on the limit cycle. Just for example, hypothetically, you can choose 0.2, 0.8, 0. Then we have chosen the initial conditions for z as 0.001, 0.01, 0.05, and so on. So then we have observed, say, up to z equal to 0.02, trajectory is going to converge to the limit cycle on the XY plane. But once z0 is greater than 0.02, trajectory will converge to the either 2 periodic solution or 4 periodic solution or chaotic attractor in the interior of the first quadrant, once the value of D2 is lying somewhere here.
Yes, I understand. Very interesting. And well, my last question, I didn't want to ask, but maybe I will. It's a little bit philosophical, a little bit provocative. So we see that this behavior strongly depends on the choice of the functional response. And if we compare with the data, as you showed in your figure, the data is very noisy. We cannot make a conclusion what function describes better this data. So we can, in fact, feed many different functions, will obtain many different types of
actually
behavior.
that data
So,
means if you refer to this data means what I showed earlier, that is this one. This is just to explain that in this case there is a possibility of extinction, but in this case there is no possibility of extinction. So this much I wanted to say. And frankly speaking, if anybody look at this data and want to think about a model, then according to my understanding, first reasonable model will be a stochastic differential equation, even no any deterministic equation, because this kind of irregularity or continuous or random variation is possible only in case we have a stochastic differential equation.
Right. So I think that we can say that it's like it often happens in modeling of complex problems. So we might be able to predict behavior of the system in a finite time interval, but it becomes hardly possible for a very long time interval. Is this conclusion?
Yeah.
All right. Thank you very much. It was really interesting. Other questions from the audience? Well, if not, then thank you again. And I think that we will have a continuation of this study, or well, of this cycle of works next week, right?
Yeah.
We will continue about also complex nonlinear dynamics. All right. Thanks again. Thanks also to our listeners. Have a good day. Goodbye to everybody.
Thank you. Goodbye.
Thank you very much. Goodbye.